I want to talk a little bit more about the two-box model for the thermohaline circulation. And I've recopied a picture of the box, the setup of the model. So there's a low latitude box with temperature and salinity, and a high latitude box with temperature and salinity. And this is forced at the surface with a moisture flux that takes fresh water out of the low latitude box and dumps it into the high latitude box. So these are atmospheric processes that evaporate water, excess water over in the low latitude, and then precipitates more in the high latitude. And that has the effect of trying to make the high latitudes fresher and therefore less dense, and the low latitudes saltier and more dense. At the same time, the heat transport goes the other way, where there's excess heat coming into the low latitude, and that makes the low latitudes generally warmer and the high latitudes cooler and therefore more dense. So there's competing effects. And so the setup of the model is to look at the variables for the density difference or the temperature and salinity differences between the boxes. And these are expressed in non-dimensional variables. So the quantity x is proportional to the temperature difference between the high and low latitude box, and y is proportional to the salinity difference between the high and low latitude box. And then x times q, where q is this quantity over here, 1 plus mu squared x minus y squared. This is the transport between the boxes, the exchange rate, and this is the heat or the heat flux in the ocean between the box from low to high latitudes. And so I've coded up these equations and showed last time that you can get multiple equilibria. I've cleaned up the code a little bit. So if you remember last time, I cut and paste the bit where I ran the model with the parameters p bar, the mean precipitation increasing in one direction and then decreasing on the way back. And now the way I did this, I implemented this by taking the p range variable, which went from 0 to 2, and then tacking onto that the reversed order of the same p bar values. And so now I can just have one loop through these values and make the plots. And I've also included an extra plot. So at after each solution, I plot both the salinity difference between the boxes, that's the y variable, the one I was plotting last time, but also this x times q quantity, which is the poleward heat transport. Because I think by looking at that variable, we get a better sense of what the climatic implications of the model setup is, which might have been obscured a little bit by the abstract nature of the model last time. So let's run it again. And here you can see the calculation going by. And so the both plots show the p-bar forcing, the freshwater flux from the low to high latitudes. Oh, can't see it. This p-bar value, which is the flux, the removal of fresh water from low latitude, and the addition of the same amount of fresh water in the high latitudes. Shown on both. And then what this plot is the salinity gradient, and this one is this poleward heat transport variable. And you can see here, as we increase p bar, the salinity gradient increases, and at some point what happens, there's a discontinuity and the solution jumps up to the other branch. And if we decrease p bar by going in the other direction, eventually there's no more solution and it falls back down here. Now this points out the interest in this in terms of abrupt climate change and catastrophic climate change. If you look at the poleward heat transport, you can see here that as we increase the poleward freshwater flux, the amount of poleward heat transport decreases continuously, but at some point there's no more solution and a slight, ever so small decrease in the freshwater transport, and the solution falls to the other branch. And that leads to nearly a factor of 4 decrease in the amount of poleward heat transport. So if this was the real Earth or real climate model, this would imply catastrophic climate change, right? We'd probably go into an ice age as we jump from here down to this other branch with so much less poleward heat transport. The high latitudes would be much colder. And conversely, the same thing happens when we're walking back down this one. If p bar is decreased ever so slightly, then we jump up to the other branch, and this time the change is even more dramatic. There's almost a factor of 6 increase in the amount of poleward heat transport. So these kinds of hysteresis and catastrophic climate change are of great importance. in climate sciences. So we would like to know if any such behavior exists in the more complicated climate system. Okay, so last time I was explaining that the behavior of the model where the solution goes like this and then seems to stop really implies that there's a curve something like this. And what we were doing is we would calculate a steady state equilibrium and then use this as the initial guess at the next time, and then use Newton's method to converge onto the branch. And then we would use this at the initial guess, increase p bar, use this as the initial guess, and then iterate using Newton's method. And we kept on doing this. This is the initial guess, the last solution. Use Newton's method, converge back onto the branch. Use the previous solution as the initial guess, Newton's method, converge onto the branch. Now, when we got close to this nose point, then we increase p bar, and now if we try to converge back to the branch no longer exists. That solution that we were always converged to no longer exists. And two things can happen at this point. Either Newton's method doesn't converge, and that's what we see with these blue points here that seem to fall off the curve. These are not actual equilibrium solution. These blue points are where Newton's method took 50 iterations and gave up and could never converge. And that's because there's no solution in the neighborhood of this point. It seems that at some point Newton's algorithm was robust enough that when I further increased p bar, it was able to converge onto the upper branch. But there's no guarantee of that. It could be that the method just fails on a different problem and we wouldn't be able to find the solution anymore. And the same thing happens when we were moving back down the other branch. If we have an equilibrium solution here and we use this as the initial guess for the next value of p bar, then we may not converge. And this happened with this point. These 2 points over here, the blue ones, are not actual solutions. So it seems that this method we were using, to use Newton's method, and using the previous solution as an initial guess for a new problem in which we slightly perturb p bar, kind of works, but it may break down in these points here, in these neighborhoods of bifurcation points, where the solution goes from having one equilibrium or to more than one equilibrium. And so we want to avoid these cases where the method stops converging and then have a way to negotiate, keep tracing the points along the branch, which we can never see over here. There's somewhere in here, there's a branch of solutions which we were not able to find. And the way we will do that is in 2 steps. The first, if we will try to improve the way we get an initial guess. So here, when we're doing the initial guess, we're just using the previous solution, but we can do better than that. Once we have the solution at a point, it's quite easy to calculate the derivative of the solution with respect to the parameter to get a better iterate. So if the branch is like this, and we have a solution here, then instead of just using the same solution as the initial guess, we can compute the gradient of the solution with respect to the parameter that we're varying. So in this case it was p bar. We can take the derivative of derivative with respect to p bar of the solution. And that would be tangent to this curve. Right, and you notice that this should be a much better iterate, much closer to the solution branch. And then our Newton's method has a better chance of converging, or at the very least, will converge more rapidly to the solution. That doesn't fix the problem when we're close to the bifurcation point here. If we're right at the tip and we compute the derivative, then if we're at the tip, the derivative is infinite. And if we multiply that by a finite p bar, then the predictor will be to go off to infinity. Right? Well, the chances that we're right at the tip are very small, but even if we're just close to the tip of the turning point, then the derivative is very big. Right? It's becoming singular, and we will shoot off to never never land, and then Newton's method is very unlikely to converge. So we want to include this gradient, and then we want to try to have a way of going around the bifurcation point. So the first thing we'll do is we'll just implement this idea of computing the gradient. So our model is this one, f, and I'm going to ignore the t variable, which is a function of the model state u, and some parameter lambda. and we want this to be equal to 0. And now we're going to compute the derivative of u with respect to lambda. So if I just differentiate this with respect to lambda, I get df du times du d lambda plus df d lambda equals 0. Now let's remind you what all these terms. This term here is the Jacobian matrix that I was talking about last time, the matrix of partial derivatives of f with respect to the components of u, and they're the following: df1 dx, df1 dy, df2 dx, df2 dy. That's this thing. And this one, du d lambda, that's du1, or dx, I guess, d lambda, and dy d lambda. Right, because u, the state u, is just x and y for our problem. And f is just f1 and f2. So we're doing a simple case with only 2 equations and 2 unknowns. But this formula would be general even if we had a bigger model with hundreds of state variables in u and hundreds of equations defining f. And lambda would be our parameter, so lambda in this case is the analog. For our case, lambda would be p bar. So the reason we like this is that here now we have an equation or a system of equation for du d lambda, and we can use this as a way to predicting the next value, our new initial iterate, right? We can say u at the new p bar at p bar plus delta p bar is equal to u at p bar. That's the solution we've already have that we've converged. 2 plus du dp bar times delta p bar. So if we have this solution and we can compute this du dp bar, we have a previous solution, and at this solution we evaluate du dp bar at p bar, at the previous value of p bar, and multiply by the delta p bar, we get an estimate. This is approximate. Right, this is a Taylor series in P, and we neglect the higher order terms, no higher order terms, and we get a new estimate. And we use this as the initial iterate for our new step in Newton's method. So we're going to implement this first before we worry about negotiating the turning points. All right, so let's implement this. So for that, I go back to my code where I have thermohaline circulation.m. Okay, so remember the way the code works. Right now, it's a MATLAB function. I check if the number of arguments is greater than 1, output arguments. Right, if I ask for the Jacobian, then I compute the Jacobian. And now, I will add an extra if statement. If nargout is greater than 2, so if I ask for 3 output arguments, then the third one will be f dp. So I'll compute this quantity here, df dp, because this is the one I need. This one from here, I didn't point this out, I can compute du d lambda will be equal to minus df du inverse times df d lambda. So this one, df d lambda, that's what I'm calling f sub p in the code. If I compute that, I've already have j, I use it in Newton's method. This is what I'm calling j, this matrix, and I invert it to get the Newton correction. So I already have the inverse of this matrix. I'll simply apply it to df d lambda and get du d lambda, which I can then use down here to construct my new initial iterate. So that's why I will pass only df dp. the derivative of the model equation with respect to the parameters. And that's easy to compute. So down here, I would add. So where's my equation? X dot is over here. So F1 sub, and there's 3 parameters, so I'll compute all of them while I'm at it. F1 sub alpha is equal to minus x minus 1. F1 mu 2 is equal to dq. Let's see, is minus x times dq d alpha, dq d mu 2, sorry. dq d mu 2 is just x minus y squared. X minus y squared. F1 dp bar is just 0. P bar doesn't appear in the first equation. And then the same thing now, but for the F2 equation. Compute the predictor over here, and then compute, maybe just corrector, and here just predictor. So this is a Taylor series approximation to where the next equilibrium state will be when we perturb P bar by perturbing by an amount dp bar. The corrector is Newton's method. Now it's just occurring to me here that there is a problem, right? As I'm moving along here, P bar at first increases when I go from 0 to 2, but then when I flip around, I'm going backwards, and then P bar decreases. So I should be a little bit more careful and not just compute P bar like this. What I'm going to do is compute P bar explicitly over here. So P bar will be equal to P bar range. I'm currently at step K, so I want K, I've already computed that one, yeah. P bar minus P bar at K minus 1, the previous one. This would be dp bar. So it's the change. Here's the mistake, I didn't put an equal sign. Equals THC TXP. Okay, so I need to call my THC function so that I can get out the f sub p. Now I already had j from the last iteration, but I will recompute it. Now what I called x here should be the previous solution, so this should be u of colon k minus 1. Alright, so I call my function. I don't need the time rate of change of the model state, but I do need the Jacobian and f sub p. And from these I can construct du dp, or partial u, partial what I call lambda, or in this case, specific case, p bar. And then I construct the predictor. And then I stick the predictor in my Newton solver as the initial guess, and then I iterate. Clear all to box. Let's see if that works. All right. Clear all, CLF to box. All right, so it seems to work nicely. The predictors seem to have helped these points that didn't converge before. We still have one over here that didn't converge. I don't know if the number of iterations changed or not. I'm going to modify my Newton's method to return the number of iterations so that I can keep track of whether convergence is faster or not. Alright, so I have the iteration number. I do compute it, but it doesn't get used. So we'll pass it out as an optional output. Right now here, when I have the now I'm going to print out the number of iterations. Fprint f it number equals percent. Let me do it one more time. All right, so iteration number seems to be 2 almost everywhere, except when we got near the nose points. I don't know if you caught it, I was just flying by. Method didn't converge, 50, and the next one 36 iterations. So these are the 2 points right around the nose point. On the way back, these are these 2. And on the way forward, there's one here and the other ones, but they all converged. So as I was moving forward, over here, the number of iterations started increasing, 3, 4, 46. But then after that, I'm on the upper branch, and now it takes only 2 iterations to converge. And on the way back, similar thing happens. I'm approaching the nose point. The number of iterations goes from 2, 3, 4. Then there's no convergence, right? Took 50 iterations, then 36, but it converged, and then after it's only 2. Now, let's go back. I should have done this first and see how many iterations if I don't use the predictor. So if I just replace U0 by the last solution, and let's see if I do any better or do the same. So I'm going to ignore this predictor. All right, let's try again. Close all, clear all, 2 box. So now the number of iterations is 3 everywhere, so it seems to take 1 more iteration than before. Let's take our P bar steps further apart to see if there's even more dramatic improvement. So P bar range, we used to have 40 points. Let's decrease it down to just 15 points. Now let's run it again. Let's get that for 2 box. So it doesn't seem to be that set up. Just 3 iterations seems to be pretty good all the time. Let's see if the predictor method will improve a little bit. So now I'm going to comment out the previous solution predictor and use my linear approximation. Clear all, CLF 2 box. Right, so they seem to be mostly 2, 2. But there's a few places right near the nose point. It seems that things get kind of brutal, right? They're pretty small. So before it was almost always, well, sometimes 4, 5, 18. All right, let's first introduce some terminology. What we've been doing, where we trace out the solution branches as a function of P bar, this is known as a continuation method, in the sense that we're trying to continuously trace out the solution branch as a function of the parameter P bar. And we call it a natural continuation method because the parameter that we're using for the continuation is a parameter that appears in the problem, namely P bar. And that's to contrast what we're going to do later to go around the turning points, where we're going to have an arc length continuation. We're going to introduce a new parameter, which is an artificial one. But first, let's review what I mean by the natural continuation. So we're given a solution branch, so we're given a solution U naught P bar naught, and by a solution we mean that f of U bar naught P bar naught is equal to 0. Remember where f is this function here, f of U and P bar is defined as where P bar, mu squared, and alpha are parameters. So U naught, P naught makes this equal to 0, which this here was equal to d by dt, right, of U. So if this is 0, then U naught, P naught are a steady state, no time rate of change. It's an equilibrium position. All right, so if we have such a point, the first thing we're going to do is we're going to try to construct a predictor, and we're going to do that by solving this system of equation. So solve df du bar du underscore, I mean. This is the Jacobian matrix of partial derivatives, and it's a 2 by 2 in our case. This is the derivative of U with respect to P bar, and that is equal to minus df du bar And that's the derivative of the equation with respect to, no, p bar here, p bar. That's the derivative of the equation with respect to p bar, the freshwater transport from the low to the high latitudes. So we're going to solve for this quantity to get du dp bar. So this is known. We can compute it if we know u naught and p naught. This one is also known. We can compute it if we know u naught and p naught. And this one is what we're going to solve for. Then we'll have this one also. And from this we can construct the predictor. And I'm going to call the predictor u superscript 0. Like the lower subscript means it's a solution. The upper one, it's not quite a converged solution yet, it's a predictor. And that's going to be our old solution, u naught plus du dp bar multiplied by p bar minus p bar naught. So this is going to be the increment in the p bar value, that's delta p bar. And this should look familiar. This looks a lot like an Euler forward stepping scheme. Instead of stepping in time, we're stepping in p bar space. So we're moving the parameter, but we're integrating the equation. So this is called an Euler forward predictor. And then, once we have our initial predictor and initial iterate, then we use Newton's method. Newton's method corrector. And that the algorithm for that is we use the Jacobian matrix at iteration I, multiplying by u at I plus 1 minus u at I is equal to minus f at u at I p bar at I. So we're going to solve this for this values for iterate for I equals 0, 1, 2, and so on until the norm of this quantity is less than the tolerance. So when I have I is 0, then I can compute u1 by solving this system of equation. If this is if this is u naught, this is going to be small, we hope, but not exactly 0. I mean, if it's 0, that's great, but if it's not, then we can get a new, better solution by correcting the old one with this new one by solving this system of equations. Right, so in Newton's method we would get this u at I plus 1 is equal to u at I minus df du bar at I inverse applied to f at u I p bar I. This is the Newton iteration. And once we've converged, the last steps 4 is to replace u bar naught by u bar I plus 1, the converged solution, and p bar naught by p bar I plus 1, the converged solution, and then go back to step 1. And then we start again, and we keep iterating. So this algorithm is looks good, right? Remember how it works. If this is the solution curve, and we have over here our first iterate, u naught and p naught. This is the p bar axis down here. So we have a particular p-bar. We're going to take a step from here maybe to here. This is going to be a fixed delta p-bar. And we take our predictor by taking the derivative of u naught along this solution branch. So we go something like this. And this is our predictor. And then we use Newton's iteration to step to a new solution, u1 p bar 1. And this iterative step here, this is Newton's method. And that's the corrector. And this is the predictor. And then we repeat. We could take the derivative at this point and take our step. We get a new predictor. And now we iterate, and this is again a fixed delta p bar. And now we start iterating, and now there's no solution necessarily close by. Maybe there's one way off the page somewhere, but there's no guarantee that we'll ever find it. And so the method will fail very often when we reach these turning points. So the solution is going to be the following. What we're going to do instead is we'll have the solution branch like this again. We have our solution u naught and p bar naught. We'll take the predictor again. But now we're not going to have a fixed delta p bar. This will not be fixed. Instead, what we'll fix is a distance along this line over here called the arc length. So then the Newton corrector is going to take us back here to u bar 1 p bar 1, u1 p bar 1. And then we take another predictor using the tangent over here. And now, even though there's no solution, we're not constrained to move only at a fixed p bar increment. It can move back to the branch. This would be u2 p bar 2. And then we take another derivative, get the new predictor, and then go back on the curve. So what we have instead are these distances here along the curve, which we're calling delta S. These are going to be fixed size. Instead of having fixed delta P's, right? The delta P's will not be fixed. All right, so this is called the arc length continuation. And so how do we compute this continuation? Well, the condition we want is that df1 dx times dx ds. So we're going to introduce this arc length s. So our problem will now become f of u of s p bar of s equals 0. And if I take the derivative of this with respect to s, I get df1 dx dx ds plus df1 dy dy ds plus df1 dp bar ds equals 0. And same thing for the second equation. And now the partial derivatives of f1 and f2 are all known. What's not known are these dx1, dx ds, dy ds, and dp ds. So for our particular problem, what we have is 2 equations and 3 unknowns. So there's going to be many solutions to this problem. It's underdetermined. And so we're free to add an extra condition. And the condition we're going to add is that dx ds squared plus dy ds squared plus dp bar ds squared minus 1 is equal to 0. In other words, we're going to insist that the arc length is equal to 1. The increment in the arc length. And in practice, actually, we will use this to compute these. This system here can define what we're calling dx ds at s equals s naught, the solution, dy ds at s equals s naught, and dp bar ds at s equals s naught. So the solution to this system is going to give us these three quantities, which I'm just going to call x dot, y dot, and p bar dot. We'll use this for the predictor, and then when it's time for the corrector, we're going to linearize this one. We're going to linearize the equation to get a simpler system. And what we're going to do, we're going to approximate this dx ds squared plus dy ds squared plus so we're going to approximate it by this new function n, and this function n is going to be defined in the following way: x dot times x of s minus x of s naught plus y dot y of s minus y of s naught plus p bar dot times, these are all multiplied here, p bar of s minus p bar of s naught minus s minus s naught equals, well, that's just this function n. We're going to try to make it equal to 0. And you notice that if I was to divide through by s minus s naught, 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 this becomes 1, which is like this one. And this is a finite difference approximation to p bar dot, right, this quantity. So this would make it p bar dp bar ds squared, and this is a finite difference approximation to y dot, so this would be dy ds squared, an approximation to this, and then same thing for dx ds squared. And so the system, we're going to use this for the predictor, and then for the corrector, we're going to solve the augmented system. So for the corrector, we construct g of u of s and p of s. S is going to be defined as f of u of s, that's our original system, plus n of u of s, p bar of s. And then we're going to apply Newton's method, and we construct the element and apply Newton's method to G. So apply Newton's method to G. So once we found this equation equal to 0, this system, then f will be 0, which means we have a steady state, and this system of equation will be 0, which means that we satisfy this equation over here on the bottom, and this will give us a finite, we're going to prescribe s minus s naught, so n, this equation here, n of u of s and p bar of s is going to be set equal to x dot times x of s minus x of s naught plus y dot y of s minus y of s naught plus p bar dot p bar of s minus p bar s naught minus delta s equals 0. And so we're going to fix, this one will be fixed delta s, so that we travel a finite distance along this arc length curve. So we're going to fix delta s, and then that's going to force us to have a p bar which is different from the previous one. This here is at s equals s naught. This is evaluated at s equals s naught. And this one is evaluated at s equals s naught. So we can compute all these things from the predictor, and then the new p will be a finite difference away from the old one, because we insist that delta s does not be 0. And to be consistent, we'll have to have a y which is different than the previous one, and the x which is different than the previous one. And this is what's going to allow us to negotiate around the turning points. So I want to show you how this works. Briefly, we can look at the MATLAB code. So I've already written it, and we can just look at what it looks like. Alright, so the code is, the calling routine is called arc length for arc length continuation. Let me comment out some things in the code before we run it. Here, let me comment this out, this, and set mu2 to be, I think we had 7.5. 7.5. Okay, so I set the parameter to mu2 to 7.5. P bar, I'm going to start at 0. P bar 0 is 0. I'm going to first apply Newton's method to find a first solution. My u naught, p bar naught, to make sure that I am on a solution. So the continuation parameter is going to be called c naught when I call the continuation code. So c naught here is p bar in my case. That's the one that I want to vary. Then I'm going to take a maximum number of 500 arc length continuation steps, or I'm going to try to vary s naught, s, from 0 to 1. So I'm going to keep incrementing, and I'll stop either after I take 500 steps, or that my arc length increase from 0 to 1 in steps of 0.04. This is my function that I want to solve, which is the 2-box Stommel model for the thermohaline circulation. Right, it takes in t, u0, which is the x and the y, and then the parameters, and the parameter I'm varying is c0 over here. It's created into a function of 2 arguments, and then the third parameter is the one that I'm going to compute the partial derivative with respect to c. It's the third one of the p. So remember how I modified it a little bit from last time. thc.m. Down here, the third input, I'm calling it k, which was 3 in this case, and then I can extract the third partial derivative. So because I'm doing a continuation, p bar is the one that I'm trying to increment as I go along the S-shaped curve, not mu2 or not alpha. If I wanted to do a continuation with respect to mu2, I would set k to 2, and if I wanted to do it with respect to alpha, I would have set k to 1. And so here I have k3 because it's p bar. And then I call my continuation code, which is going to find the whole branch of solutions and store it in B. Inside of B, I'm going to show the plots here. I have B is going to be 3 by n array, so n columns, which n will be a maximum of 500, and the first row will be the x values, the temperature difference between the boxes. The second row will be the salinity differences between the boxes, And the third row will be the values of P bar, the mean moisture transport from the low to the high latitude box. And so we can then plot we can extract X, Y, and compute Q and P bar, and then make the plot. So the first plot will be P bar, the heat transport, Q times X as a function of P bar. And the next one will be a plot of the salinity gradient as a function of P bar. And this I want to comment out. Alright, so let me run this code so you can see how it works. Arc length. This I comment out. This I comment out. The rest, I think the rest is good. Arc length. Alright, so the solution, it computes very fast. This is the poleward heat transport as a function of P bar, and this is the salinity gradient. And you can see here these two nose points, and it fills in the solution in between. If I could put in a little symbol so we can see how many solutions it computed. S. Let's see if that works. And maybe I don't need to take so many steps. 200. Clear all CLF arc length. Right, so this is the solution. So you can see all the little squares are all the different solutions that I computed along the branch, and has no difficulties negotiating around these turning points and following the solution branch. So what does this continuation code look like? Let's have a quick look. So we pass in the function we're trying to solve, f, an initial solution, x naught, the parameter, the initial p bar parameter, which in here is going to be called c naught, ds, my arc length increment that I want to take my steps size of, the last point, as far the maximum arc length, I'm going to try to compute the solution, or the maximum number of continuation step. Plot function is a way that you can use this to make some plots along the way, but I'm not going to use this argument. Okay, so the first thing we do is we make sure that our solution we passed in, x naught and c naught, is indeed a solution. So we apply Newton's method to it, and we iterate to make sure we get a converged equilibrium solution on the solution branch. If the I flag from Newton's method is 1, that means the method didn't converge, and then I'm just going to abort right there and then. But if not, I'm going to replace x naught, the one we passed in, with the one that I know with xq, which is the one that we just got from iteration using Newton's method. So I know now that x naught is on the solution branch for the parameter c naught. Then I solve the predictor equations using this df dx, df dp, and the x dot and c dot. So the first part is to try to solve for the x dot and the c dot. So x dot and c dot in the code here, x dot is really what I was calling u dot in my equations. So what I'm calling x dot in the code will be really u dot, which means x dot, y dot. Alright, so it's a little bit confusing because the functions I'm using in the code, the names of the variables are a little bit different than what I tried to explain here. So I compute the predictor, and once I have the predictor, I can start my loop, my continuation loop. So that's stored inside this while loop. And there's two steps. The first time, so I have one predictor step that happens outside of the loop, and then I do a corrector. So I call Newton's method on the augmented system G. G is constructed down here, and it is constructed using the F that I want, plus this N equation for this pseudo arc length, which has the u dot times u minus u naught. So that would be this equation over here. So the u dot is x dot, y dot, and p bar dot, and u minus u naught is a vector, a 3 by 1 column vector, and it'll have xs minus x naught ys minus y naught, and p bar s minus p bar s naught, minus ds, and that's the finite ds. And since I'm going to apply Newton's method to this g, I need to have the derivative of g. So that derivative of g is computed right here. But to show you what it looks like, the Jacobian matrix of g, it's, remember, g of u and p bar is f of u and p bar n of u and p bar. So if I compute the Jacobian matrix of this one, there's now going to be three equations. There's two in this one and one here. And that's the same thing as this first row is really the f equation, so it's df1 coming from that equation, then the second equation of f, and then the last equation, dn dx dn dy dn dp bar. And inside of here you'll recognize that this block is this the Jacobian, right? This is the Jacobian matrix of partial derivatives of our system. This one, this column over here, right, that's just the derivative of f with respect to the parameter, df dp bar. And down here, this dn dx, this, given that n of u and p is equal to x dot delta x plus y dot delta y, this is times here, plus p bar dot times delta p bar minus delta s equals 0. These things are all known. These are known from the predictor. This is evaluated at s equals s naught, at s equals s naught, and at s equals s naught. And so if I take the derivative with respect to x, remember delta x here is x minus x naught, delta y is y minus y naught, and delta p bar is p bar minus p bar naught. When I take the derivative of this with respect to x, these x naught, y naught, and p bar naught are constants, and all I'll be left with, so dn dx is just going to be equal to x dot at s equals s naught. dn dy is going to be y dot at s equals s naught, and dn dp bar is going to be equal to p bar dot at s equals s naught. And so this is what we have in here. We have the x, the u dot here was solved. So to get the predictor, I take this system here and I solve this one. So this is the predictor system of equations, and I'll just focus on the last equation. That's like taking this dotted with that, which would give me x dot naught delta x plus y dot naught delta y plus p bar dot delta p bar equals delta s. And if I divide through by delta s, what I get is x dot naught times the new del dx ds. This is an approximation, so that's like x dot 1 plus y naught dot, that's the old dy ds, times the approximate y1 dot dy ds plus p bar dot naught, there should be a naught here, and this is like a new p bar dot 1 is equal to 1. And so in the equation over here, right, I solve for u dot by taking the dg du1 and I invert here 1, 1, 1, so I've divided through essentially by delta S, delta S, delta S, delta S, and this makes it a 1. And then I want to make sure that my solution, my new one, is normalized, because the condition, right, I want to make this sure that this is equal to 1. So over here, I compute z, which is the norm of this thing, and then I divide u dot 1 by the square root of the norm, so that now I'm sure that u dot 1 dotted with u dot 1 is equal to 1. Then I increment my arc length, I compute the predictor, and I save the solution, the last solution, and I go back and do another corrector step by calling Newton's method. And if I converge good, I skip this bit, and I keep predicting and stepping along. Okay, so that's how the algorithm works. Let's run it one more time so you can see what it does. Arc length. That's the solution branch. And now what I want to show you is what happens when you have two parameters, in this case mu2 and p bar. So mu2 is the parameter that appears in the parameterization for how the flow depends on the density difference between the boxes. And if mu2 is 0, then my model becomes a linear box model, and there should be only a unique solution. So what I'm going to do is I'm going to compute the solution for a whole range of mu2s, and a whole range of p bars, so we can see what the solution looks like in a two-parameter space. So let's go to arc length code, and I have this. I'm going to take 60 steps in mu2. I'm going to range it from 0 to 20, and I'm going to step through all the different values of mu2. I don't need the 7.5. And then I'm going to save the solution from each of these continuations. So I prescribe mu2, and then I'm going to do a continuation with respect to p bar to find the solution for a whole range of p bars. Then I'm going to increase mu2 and do another range of p bar solutions. And then we can plot the solutions as we go. And then save everything. So let me run it. CLF arc length. So you can see the solution bending as I increment mu2. Right? mu2 started at 0. Let me try it again. CLF arc length. Notice here the mu2 is increasing and the solution is bending, becoming as we increase the nonlinearity. And then we can plot it. All these solutions, I've saved them in this structure S. And then we can do plot cusp. Oh, I should save it. Save cusp.mat S. And then the code plot cusp.m just extracts all these different solutions, plots it so that X is the mu2 axis, Y is the p bar axis, and Z is the salinity gradient difference, the Y variable. And so let's plot what it looks like. Plot cusp.m. And you can see here the solution, this is p bar, this is mu2, and along the vertical I have Y, and you can see how the solution kind of folds over on itself. And out here, if I'm increasing p bar, there's no fold, the solution changes, but there's a unique solution because mu2 is 0 at this end and there's no nonlinearity. But as I start to increase mu2, at some point the nonlinearity is strong enough and there's this folding of the solution, and it folds over on itself, and inside this wedge-shaped region over here, then I have multiple equilibria. I have a solution on the bottom sheet, one on the intermediate, the middle sheet underneath, and then one on the top. And I can kind of rotate around to try to show you. Right there you can see the cusp, where you have the multiple equilibria. All right, so that I think concludes my lecture on the Stommel box model. And let's quickly go through the things we've done. We've formulated a box model for the thermohaline circulation, a very simple box model. We showed how to non-dimensionalize it, how to time integrate it using Euler forward, and how it converges eventually to a steady state. Then we've shown how to find steady state solution using Newton's method. We've showed how to use a natural continuation to try to vary a parameter and find all the solutions, but that this has problems when we get to the turning points where the solution folds over on itself. So then we devised the arc length continuation method to go around the turning points, and so that we can trace out the solution branches. And I guess there's one last thing I need to talk about, which maybe I can do in another video, is that the three solutions, if I'm on the bottom branch, this is a stable solution. If I'm on the middle branch, if I initialize it there, then du dt is 0, but if I ever perturb it ever so slightly, then the solution will drift away to either the upper branch or the lower branch. So the middle one is an unstable equilibrium. But the two other ones, the one on the top and the bottom, those are both stable. So the Stommel box model has multiple stable equilibria and one that is unstable, the one on the middle. But we can discuss that another time.